Hey Maya.
Hi Matt, hi Sha. It's so nice to see you guys.
Yeah, nice to
Hi,
see you.
Maya. Hi,
How are
Matt.
things going?
Good. Yeah, the thing I'm talking about today got accepted yesterday, so
Oh,
Oh, that's super
congrats.
exciting.
yeah.
That's great. Is this isn't the salinity stuff that we've talked about, right?
This is the PMOC solar. Uh,
Okay, cool.
there is salinity in there.
Oh, perfect. Let me open up share screen. I'm gonna make you a co-host, Shah. Hi, Florian.
Hi.
Hello.
Um, do we want to quickly just make sure everything looks fine in terms of screen sharing? Do you want to go first,
Yeah,
Maya?
sure. Yeah, I can gonna go ahead and try. See,
Oh,
you should now be in my screen, but not the right one, I guess.
okay, yeah, we are seeing your screen.
Is that the
Cool.
correct view, or is that the
Yeah, that
perspective
looks
view?
great.
Perfect.
Okay, Maya, do you want to try? Looks good.
Cool.
Easy. Okay. You would not believe how difficult it can be some months to to get it.
We have the COVID experience.
Yeah, I'm sure you guys have just used a lot of Zoom too. So are you finishing up soon, Maya? Is that yeah.
Probably defending in January.
Oh, that's exciting.
Mm. You have any plan after?
We have an interesting climate and health postdoc here at Princeton, but I'm looking for
Uh-huh.
New York things too.
Nice. Oh, we have another Florian.
Sorry?
I guess we got two Florian here.
Do we?
Uh-huh.
Ah, yeah.
Hello.
Hi. So Andrew did the organizing for this one, but I guess he's traveling at the moment. So
Mm.
appreciate him pulling everything together. Hi, Sean.
Have we decided who is gonna go first?
Um, I figure we can just go in the order that Andrew wrote in the email.
Okay. Do you want
Sean,
to
do
make
you
sure,
want to
Sean?
share screen really briefly if you're there quite yet? Where did he go? Oh,
He's still here,
yeah.
but
Well, we usually start a couple minutes past the hour anyways. Hmm. Well, I've asked Sean to. Oh, hi, Sean.
Hey, Sean, can you hear us?
Yeah. Can you hear us, Sean? I'll take that as a
You are
no.
muted.
While
He's
we get
muted.
this,
Here,
yeah, while
right?
we get this figured out, maybe Maya, you can go first. I'll introduce us, and we'll just start with you.
Sounds good.
Okay. All right, so let's get rolling. Welcome everyone to the 45th ECS and Cloud Feedback Virtual Symposium. I hope everyone enjoyed their summer break. Today we have three 15-minute talks from Sean Cohen, Maya Chung, and Florian Roemer. Just as a reminder of how this works, although many of you have attended before, we're going to have three short 15-minute talks. We're going to have about 5 minutes for questions after each. And if we have time, we'll have a short general Q&A. Please type your questions or comments into the chat at any time. But if you'd prefer to ask your questions live, raise your hand and we'll unmute you. If anyone has some exciting work that they'd like to share at a future symposium, please reach out to us and we'll get you scheduled. And you can find videos of our past talks, sign up for the mailing list, etc. on our website. So let's start with Maya.
Great. Thanks, Matt. All right. Well, thanks so much for the invitation. This is really exciting. I'm here to present some work that we've done that was recently accepted in GRL like yesterday. And we looked at how two climate models cooled very differently in response to the same decrease in solar radiation. And a big part of this difference was the ocean's role in modulating climate. So if you think these plots of sea ice cover from these GCMs are cool, hopefully you'll like this talk. But first of all, why do we even care about how the Earth's climate cools? Cooling has been relatively less studied than warming, especially in recent decades. But climate cooling is relevant to paleoclimate and also potentially future climates, hopefully if we mitigate greenhouse gas emissions, and could potentially be relevant to geoengineering efforts to cool the climate. So there were a lot of studies in the 60s and 70s that looked at this question and the question of how does the climate cool versus warm. Here's an example from Weatherald and Manabe, 1975. And in this example and in a lot of examples from this time period that use relatively simple models, they found that for the same magnitude of forcing, the cooling response tended to exceed the warming response due to the asymmetry of the ice albedo feedback. And there have been a couple more recent GCM studies that have applied this sort of idealized cooling and warming forcing to more state-of-the-art GCMs. And they've also found that the ice albedo feedback is important, as well as the lapse rate feedback for the instability under cooling. But relatively few studies have been done with these state-of-the-art coupled atmosphere-ocean GCMs with dynamic ocean, and very few have compared different GCMs under this idealized forcing. So we think that the dynamic ocean might be important for understanding climate cooling for many reasons. One is a very simple reason, which is stratification. So if you warm the ocean surface, that acts to stratify the ocean. That's going to create a sort of short-term fast response near the surface, but then takes longer to equilibrate with the deep ocean. Whereas with cooling, that destabilizes the ocean, and so you'd get sort of the opposite response. Circulation, for example, the Atlantic Meridional Overturning Circulation, or AMOC. Many studies have found that with cooling to warming, the AMOC response is non-monotonic. It has different transient and equilibrium responses, and often depends on regional temperature and salinity changes, and a lot of these things could vary between climate models. In addition, ocean heat uptake and ocean heat uptake efficiency, which is the amount of ocean heat uptake per change in surface warming, has been found to vary a lot across models. And so if you're conducting relatively short experiments, the early experiments were just a few years, but now we do multi-century experiments, even a few centuries might not be able to encompass the full ocean response. So these are the types of questions we explore in this study. So here's our experimental design. So the experiments that we conduct are abruptly changing the solar constant by plus or minus 1, 2, 4, and 6%. So we apply this to a 1860 control, and we run the experiments anywhere between 300 to 1900 years, depending on what's important and interesting. And we apply this to two models, so sort of newer model and an older model from GFDL, from a common development tree. The newer model is the forecast-oriented low ocean resolution CM 2.5 model, which we call FLOR. It has the same ocean resolution as CM 2.1, but a higher resolution atmosphere, 50-kilometer atmosphere versus a 2-degree atmosphere. And these models, although they're from the same development tree, they are different model versions. So there's many things that are different between these models, parameterizations, etc. So sometimes it's a little hard to pinpoint exactly what is going on, but we do our best in this paper. And just to orient you, these are the key takeaways from the study. So we find that the responses of both models are similar under warming, but they have really divergent responses under extreme cooling, especially 4% and 6%. FLOR has a more runaway type of cooling versus CM 2.1, which has a more gradual cooling. And a big part of the story is that the more stable model, CM 2.1, develops a Pacific meridional overturning circulation, which does not exist in our modern climate. And this acts to stabilize the climate, as well as CM 2.1 having higher ocean heat uptake and ocean heat uptake efficiency. And we think that the PMOC formation comes from differences in salinity stratification in the North Pacific, which is something that other studies have found in different ways. So let's just start simple and look at the time series of global mean surface temperature across all these experiments. And these experiments are very interesting too. There's much more to do with them than I'm showing here. But the big takeaway from this figure is FLOR's dramatic cooling under 6% and 4%. Compared to CM 2.1's much more gradual cooling. The X's indicate where the models crashed, so we couldn't figure out how to run them any longer after these points. Also, we ran 4 ensemble members for minus 6% solar in CM 2.1, and they all had this gradual behavior. None of them dropped off the way that FLOR did. So we computed the total radiative feedbacks to sort of understand the stability of the system, and just looking over time with this like sliding window regression that we did, we found that FLOR had more unstable radiative feedbacks compared to CM 2.1. CM 2.1's radiative feedbacks were actually unstable as well, especially in the minus 6% solar case, but just less unstable than FLOR. So in addition to this, we looked at the ocean's role as sort of a stabilizer, and we did this in a couple ways. We looked at the ocean heat uptake efficiency, which is the change in ocean heat uptake per degree surface warming. And so the ocean acts to stabilize in both of the models, but we found that CM 2.1 tends to have greater ocean heat uptake efficiency. Another way to think about this is looking at the ratio of the deep ocean heat uptake to the upper ocean heat uptake. So a higher ratio would indicate that the deep ocean is responding more to the surface temperature perturbation. And we find that across all the extreme warming and cooling experiments, CM 2.1 has a sort of greater deep ocean response, a greater heat uptake, which could also help to stabilize the model. So then we used the kernel method to decompose the feedbacks, and we found that the ice albedo feedback seemed to be the one that explained the difference between the models the most. So this plot is showing the feedbacks over time, and Fluor's ice albedo feedback really became very unstable as opposed to CM 2.1's. So then we looked at the sea ice, and we found something interesting, which was that at the beginning of the runs, Fluor and CM 2.1 look relatively similar, but as you go a couple centuries in, there's actually sea ice retreat in the North Pacific in CM 2.1, even though it is really cold in the model. So why does that happen? We find that there is a Pacific overturning circulation that develops in CM 2.1. It actually starts developing almost immediately, and the difference between CM 2.1 and 4 is pretty evident a few decades into the run. So here's the stream function. Here's what it looks like. Oops. And this is about twice as strong as the present day AMOC. So there's a really strong PMOC that forms. We show the PMOC strength often in terms of meridional heat transport across 40 north in the Pacific. So this is indicating how much heat the PMOC is bringing northward. Eventually, the PMOC collapses in both of the extreme cooling runs. And interesting things happen there that I don't have time to talk about. Fluor actually does develop a PMOC, a much more constrained PMOC and weaker PMOC later into the runs, but because it's sort of frozen over and collapsing, the PMOC is acting on a weaker temperature gradient, so it's not as efficient at transporting heat northward. Okay, and so when we look at the sea ice at the end of the Fluor run, this is what it looks like. This is what I showed on the title slide. CM 2.1 is just nowhere near that level of ice. When we run CM 2.1 about 2 times longer, it starts approaching that level. By this point, the PMOC has collapsed, but it doesn't quite reach the same point, or at least we're not able to run it that long. Okay, and then finally, why does the PMOC form in CM 2.1 and not Fluor? So we have a couple of hypotheses for this, which may all be related or acting at the same time. The first is that the models have different vertical mixing schemes and vertical diffusivity in the ocean, which might make CM 2.1 more conducive to vertical mixing. So we see that over the first few decades of the -6% solar experiments, as the PMOC grows, which here I'm showing in terms of meridional heat transport, the North Pacific vertical diffusivity in CM 2.1 grows a lot. This is in the North Pacific Ocean. So vertical diffusivity is basically an indicator of mixing that can be driven by both the atmosphere and the ocean. But since winds and E-P were very similar between the models, we think it's mainly driven by the ocean. So another hypothesis is another reason for the CM 2.1 PMOC could be because CM 2.1 is less stratified than Fluor in the mean state in the North Pacific, which could make it conducive to vertical mixing. So here I'm showing density stratification as a function of depth in black. Here's for CM 2.1 and Fluor. And then these bars show the differences between them in the upper ocean and the deeper ocean. And the salinity and temperature contributions to the stratification are shown in blue for salinity and red for temperature. So in CM 2.1, the upper ocean has a larger temperature inversion, which makes it less stable than floor. Also, in the deep ocean, CM 2.1 has lower salinity stratification, which potentially ends up mattering when we start talking about the response. So getting into CM 2.1's response to the cooling, CM 2.1 initially cools more than floor and forms more ice before the PMOC comes and melts it. So this results in brine rejection, which destabilizes the salinity stratification in the North Pacific. And once that happens, as the mixing sort of ramps up between the upper and deep ocean in CM 2.1, it lowers the stratification even more in salinity, driving more mixing, feeding into the PMOC, drives more mixing. So eventually we get this state where there's just very little stratification in the whole water column. This is in contrast to floor, which maintains its halocline in the upper ocean and maintains salinity stratification in the deeper ocean. So there's less vertical mixing and no PMOC. Okay, so here are the takeaways. We had 2 GFDL climate models that responded differently to solar reductions. I think the takeaway from this is that controls on sea ice growth mattered a lot for the response in these models, and especially the ice-ocean interactions. The ocean heat uptake efficiency and transient PMOC lended stability to CM 2.1 especially. And here what's kind of interesting is that not only was the dynamic ocean response important, but it was both rapid and long-lasting. So there were changes happening on the scale of decades and also on multi-century millennial timescales. Finally, the PMOC formation was sensitive to salinity stratification in the North Pacific. These salinity differences were potentially due to subtle differences in ocean vertical mixing parameterizations, as well as the mean state stratification, and eventually led to large impacts on global climate. So things that we think might be small scale or regional could have dramatic impacts. So our updated preprint should be available soon on Open Archive, and feel free to contact me. Happily welcome any feedback or questions. Thanks.
Awesome, Maya. Do we have any questions from folks? We have a few minutes for questions. Feel free to either put your hand up or put it in the chat. So a question that I have, Maya, is, so the difference between floor and CM 2.1 is not just the atmospheric resolution, or so they also have different mixing parameterizations. But do you think that it's those differences in mixing parameterizations, or is it that, you know, you have a higher resolution atmosphere which affects the mean state of the ocean more readily?
I'm honestly really not sure where the mean state differences originate from. So it could be the atmosphere, but there's so many differences between floor and CM 2.1. Like almost everything is different. So yeah, it's not just the mixing. It could be many, many things. So that would
So
be
really the only similarity between the ocean is the resolution.
You could
Well, maybe that's,
potentially
yeah.
say there's just a lot of things that are
Okay.
different. There are some things that are similar. It's from a common development tree, but a lot of things like ice-ocean interactions and things like that could be very different. Yeah.
Cool. Gavin, do you want to unmute yourself?
Hi, yeah, thanks. I'm kind of interested in why models crash, and in trying to understand why they've kind of gone beyond their zone of applicability.
Yeah.
And you are kind of stress testing these models quite efficiently. So do you want to give a little bit of an update on what is causing the unfixable crashes in these cases?
Sure. Yeah, we talk a little more about this in the paper. But there's yeah, just some radiation issues. Sometimes when temperatures get really cold, the water vapor lookup table, I think, gets really difficult to use. And also we had some issues with layers in the surface ocean getting compressed under cooling. So there were lots of different reasons. There also on the warming side, there were some crashes where maybe like some bodies of water had evaporated or something. So yeah, definitely fun to stress test these models. But yeah.
And Thorsten, do you want to unmute yourself?
Sure. Hi, Maya. Very nice talk. I can certainly relate to all your issues with the crashes. So I was just curious, that what seemed to be like it's not about the core of your work, of course, but there seemed to be like a qualitative difference in how they responded around the instability. Like one was like dropping off dramatically in temperature, and the other one was kind of just continuing on
Yes, yeah.
the same slope. Do you have any ideas about what that means or why?
Yeah, here. So you're talking about this sort of drop
Exactly.
off. Yeah,
Yeah.
this elbow
On one of the
versus
next
full
plots,
linear.
it seemed like they were both negative feedback, positive, I guess, unstable. Um,
Yeah, the feedbacks, they became more like gradually unstable in CM 2.1. And then there's sort of a turnaround here. Yeah, I haven't looked into all of the aspects of this. The only thing I could, and also something interesting is that floor seems to have this like step kind of in both of the models, maybe like a two-step structure. I don't know what that is. Originally, we thought it might have been like the Drake passage closing or something, but we haven't gotten into enough detail with it. I know there's a sort of drop off here and here in CM 2.1 that corresponds to the PMOC collapsing. But other than that, I don't have too many insights. That would be great future work.
Awesome. Nodder, so in the interest of time, we're gonna move on. So maybe you can put your question for Maya in the chat. But thank you, Maya. And we're going to move on to Sean next. So Sean, do you want to share your screen?
Hi, everyone. Thanks for your patience before. Sorry that it took a little while to get my audio working. Can everyone hear me okay now?
Yeah, sounds good.
Wonderful. Let's just give this a shot then.
Looks
Great.
great.
So everyone can see my screen?
Yep, perfect.
Awesome. So hey, everyone. Thanks for coming to hear all the great talks lined up today. My name is Sean Cohen, and I work with Lorenzo Polvani and Robert Pincus at Lamont Observatory. And I'm going to speak about some of the work that we've been doing on stratospheric cooling. So one of the effects of increasing atmospheric CO2 is that the surface and the troposphere warm, but a less commonly discussed effect is that increases in CO2 also cool the stratosphere. And this insight goes all the way back to the early climate models of Manabe, and it's one of the most robust signals of CO2-induced climate change. Oh, there we go. And so additionally, because this cooling happens on much shorter timescales than the warming of the surface and the troposphere, observations of this cooling have also served as an early indicator or fingerprint of human effects on climate. And then finally, because stratospheric cooling is also known to amplify the radiative forcing of CO2, it acts not only as a harbinger, but also an accelerator of warming at the surface. And so we can ask the question, why does the stratosphere cool? And at the moment, we have a rather solid qualitative explanation for why this process occurs. Because the stratosphere is in radiative equilibrium, long wave cooling by CO2, water vapor, and ozone has to be balanced by shortwave heating by ozone. And so what that means is that as atmospheric CO2 increases, long wave cooling by CO2 is also going to increase, causing the stratosphere to cool in order to remain in radiative equilibrium. However, unfortunately, we don't really have a great quantitative theory to explain qualitative or to explain stratospheric cooling. And so this leaves open a lot of pretty fundamental questions about this process. Namely, why does the stratosphere cool more aloft than it does below? Why does a doubling of CO2 yield roughly 8 Kelvin of cooling at the stratopause, all the way down to almost no cooling at the tropopause? And why does stratospheric cooling increase the radiative forcing of CO2 by about 75%? And so our work focuses on answering these three questions using a somewhat ground-up theoretical approach that builds on a lot of previous work. So to begin, we can consider the long wave emission by CO2 at some pressure level. And so under the cooling to space approximation, long wave cooling by CO2 is going to be largely proportional to Planck emission at that temperature and wave number. And so what that means is that as stratospheric temperature increases, there will be greater long wave cooling coming from the CO2 band. Additionally, long wave cooling by CO2 is also going to be proportional to this quantity L, which effectively measures how many wave numbers have roughly near unity optical depth at the pressure level that we're considering. And so what this means is that, the more wave numbers that we have near unity optical depth, near tau equals 1, the more long wave cooling we'll see coming from the CO2 band. And so we somewhat cheekily call this fraction, or this quantity L, the Goldilocks fraction, since it represents the fraction of the CO2 band that's neither too optically thick nor too optically thin to contribute to long wave cooling by CO2. And so we can ask the question, how does Goldilocks fraction change with CO2 concentration? And so what we find is that Goldilocks fraction is controlled by the spectroscopy of CO2, somewhat unsurprisingly. And so here we have the raw mass absorption coefficient of CO2 across the CO2 band. And if we sort it from largest to smallest on each side of the band, and then bin it by mass absorption coefficient, we can effectively count how many wave numbers have a certain mass absorption coefficient. And so while lower mass absorption coefficients tend to be rather plentiful, higher mass absorption coefficients are less so, as they fall off to 0 near the center of the tube band. So that as they fall off as the center of the CO2 band narrows. And so typically CO2 spectroscopy is parametrized using this sort of linear or triangular approximation. However, in this specific case, this fails to capture the narrowing of the band center. You can see this in sort of the rapid drop off in the orange line as compared to the binned gray line. And so in order to capture this more gradual decay, we can just slightly modify this parameterization in order to do so. And if we use the tau equals 1 emission level approximation, we can effectively capture how Goldilocks fraction changes with pressure and CO2 concentration across the depth of the stratosphere. And so what we see is that, as CO2 concentration rises, Goldilocks fraction is going to change a lot more in certain parts of the stratosphere than others, which is going to cause cooling to be greater, in some places in the stratosphere compared to others. The other thing that we have to consider here is the modulation of emission by CO2 due to emission in other parts of the spectrum. So as CO2 concentration rises, cooling by CO2 is going to increase, as shown by the difference between these two lines here. But cooling by ozone and water vapor, these other set of lines, will actually decrease in response in order to maintain radiative equilibrium. And so we can approximate this response by simply assuming that the long wave cooling rate of water vapor and ozone will change linearly with temperature at each pressure level. In reality, the spectroscopy of ozone and water vapor deserve their own treatment, but this is sort of a good first approximation to this process. And so what we find is that together, these relatively simple spectroscopic mechanisms can explain the magnitude and vertical structure of stratospheric cooling. Qualitatively, we find that the fractional change in stratospheric temperature can be written as follows here. where it'll be proportional to the fractional change in Goldilocks fraction to a source scaling, which measures how much some change in temperature induces some change in Planck emission by CO2. And then also to what we're calling a spectral efficiency, which measures how much some change in stratospheric temperature induces a change in the cooling of CO2 versus how much that same change in temperature induces cooling in the entire spectrum as a whole. And so what we find is that, this relatively simple equation gives us a good first order estimate of the magnitude and vertical structure of stratospheric cooling. Here we're just comparing it to these solid lines, which are somewhat more complex simulations using line by line radiative transfer calculations in the RCE model Conrad. And so what we can do is use this relatively simple formulation to again explain where the magnitude and vertical structure of stratospheric cooling come from, and even to get a pretty good first order estimate of why a doubling of CO2 gives you, roughly 8 Kelvin of cooling at the stratopause. And then we can move on to ask sort of the broader question of what do these findings imply about stratospheric cooling or about the radiative forcing of CO2. Here we can sort of think about this problem somewhat simply, somewhat schematically by thinking about the emission at different wave numbers in the CO2 band. Here in black, we have the emission at different wave numbers before some doubling. And then in red, we have what changes about the emission as CO2 is increased. And so the dotted line shows what happens if we don't allow the stratosphere to cool. Everything just shifts upward uniformly. However, if we do allow the stratosphere to cool, then all of these emission temperatures coming from the stratosphere will be shifted downwards, and we want to account for those effects. And so in order to do that, we can kind of think about two limiting cases. On the one hand, we can think about the really intuitive case of no stratospheric cooling. This is actually equivalent to the case where eta, the spectral efficiency, is actually equal to 0. That means that for some change in temperature, you're going to have a lot more change in emission by ozone and water vapor than you do for CO2, which will just damp the cooling down to 0. And then on the other extreme, you have what you can think of as maximum stratospheric cooling, where all of the emission is coming from the CO2 band. And so what'll happen is that basically the stratosphere will cool such that the reduction in emission exactly balances the increase in emission due to the widening of the CO2 band. And so all you'll get is just the masked surface emission in this case. And so what we see is that the actual eta of the atmosphere is roughly between these two extremes. And we can use that to understand where this 75% increase in the radiative forcing of CO2 due to stratospheric cooling comes from. So here we actually have a plot of this occurring. On the x-axis, we have the initial CO2 concentration. And then you can think about both the instantaneous radiative forcing and the effective or stratosphere adjusted radiative forcing that occurs after a doubling of CO2. And right here, what we have plotted in gray is this maximum that occurs, this theoretical maximum, assuming that eta is 0. And because eta is, roughly a half, what we would expect is that ERF will fall roughly halfway between these two extremes of IRF and ERF max. And so because IRF is roughly 2 watts per meter squared, ERF is roughly 5 watts per meter squared, we get that the actual ERF will be, roughly halfway between these at 3.5 watts per meter squared, roughly speaking. So what are the central takeaways here? The big picture here is just that CO2-induced stratospheric cooling and the associated adjustment to the radiative forcing of CO2 is going to be controlled by these relatively simple physics. On the one hand, the spectroscopic properties of CO2, namely this Goldilocks fraction, are going to dictate how much the emission by CO2 is induced to change for some change in concentration. And then it's also going to depend on the extent to which this emission by CO2 is modulated by emission in other parts of the spectrum by ozone and water vapor, or this so-called spectral efficiency. And so if you're interested in learning more about this, we have a preprint available we just submitted. So if you're interested, let me know. I'd be happy to tell you more. Thanks so much for your time.
Awesome. Thanks, Sean. Questions from the audience?
Nope.
Feel free to raise your hand. Gavin has a question. Do you want to unmute yourself?
Hi, thanks. When you're talking about the radiative balance in the stratosphere right at the beginning, I think you kind of missed out one key component, which is the upwelling long wave in the absorbing bands for the CO2, right? And that sees a big decrease in a 2 times CO2 world, which is one of the reasons why the divergence of energy in the CO2 band itself in the stratosphere is so large, right? And I don't think that that's negligible.
Great question. So what we actually found was that the cooling to space approximation, which I think is what you're talking about, let me see if I can go back to it real quickly. This approximation we made relatively early on right here.
Yeah.
So this approximation, the cooling to space approximation, which has been made in a bunch of other literature, you're absolutely right, does break down near the tropopause where you have this temperature inversion. However, in the bulk of the stratosphere, what we find is that it actually, works very well as a first order approximation for how much cooling you get by CO2 in the bulk of the stratosphere. And so even though the temperature inversions at the stratopause and tropopause disrupted a little bit, again, we find that this is a pretty good approximation. And then furthermore, the changes in Q with temperature and with CO2 concentration tend to be an even better approximation, since near the stratopause and tropopause, the changes in temperature just above and below those temperature inversions are actually roughly similar. And so the changes in Q with Q and big Q with little q tend to be pretty constant.
Right. So I mean, I'll accept all of that, but I don't think that was quite the point I was making. So if I have a spectrometer in the stratosphere pointing down and I do an instantaneous 2 times CO2 increase, what I see is that there's a decrease in upwelling long wave at the CO2 wavelengths, because it's being absorbed in the troposphere. So it's not a local issue associated with the tropopause. It's an issue of like what's the radiative flux in that frequency that's coming up, and that goes down a lot because everything gets increasingly blocked in the tropopause. Right. And so that has to add to the divergence of flux anywhere in the stratosphere or even in the mesosphere, due to both, the increasing efficiency of emission to space, but also a increasing loss of absorption from the bottom.
So I think what you're talking about is the intra-atmospheric exchange terms. So my understanding is, so I guess if you're talking about some pressure level in the middle of the stratosphere, you're absolutely right. You will see, changes in how much emission you're seeing from, the atmosphere below it. But the idea is that the cancellation of that with all the other inter-atmospheric exchange terms, and then also with the surface, means that the cooling to space gives you a first order approximation for what the net change in cooling by CO2 will be. And so because that's what we actually care about, you can make the cooling to space approximation. So my understanding is that, even though you have an increase in emission from below, you'll have a decrease in emission from above, which roughly cancels. Does that make sense, or am I still not understanding your question?
I think that makes sense. Let me think about it a little bit more. I'll send me your preprint and I'll dig into it some more. Thanks a lot.
Yeah, absolutely. Thanks for the question.
Awesome. And we have time for one quick question. Moritz?
Hi, thanks. This was really interesting. I had a thought about, like, in the real stratosphere, we're going to see an additional dynamic term from the Brodobson circulation that's also going to cause dynamic adjustments to the temperature. And I wonder if you've thought about the effect of this. Would it be small or large, or?
That's a great question. So in this first pass, really what we looked at was just changes, assuming that the concentration of all the other gases in the stratosphere are held constant. So in the global mean, heating by the circulation will obviously cancel out, but you're absolutely right that if that causes changes in the concentration of ozone or water vapor, those are important feedbacks that we would need to consider. Our reading of the literature suggests that those contributions are decently small, or at least what you get, the predictions you get for global mean stratospheric cooling from these RCE simulations that hold everything constant except for CO2 tend to be in pretty good agreement with sort of more comprehensive simulations. But you are absolutely right that that's the next feedback we would love to explore is, there's going to be feedbacks of temperature on ozone. Like you said, circulation feedbacks will affect how much how much water vapor is kicked up into the stratosphere. And it'd be interesting to understand those feedbacks as well.
Now, just to quickly clarify, it's not about this change of the concentration. The argument is more about the direct dynamic cooling term, but I can write you about it, and I think it would be cool to explore this in a 3D climate model. Anyway,
Okay, yeah, my understanding is that it would cancel out in the global mean, but
yeah,
we can talk about it a little bit more.
right.
Awesome. All right, thanks, Sean. That was a really nice talk. And we're gonna wrap up today with Florian.
Yeah, hi. Thanks for having me. So today I'm presenting work together with Stefan Bühler and Carmen Ang on how to think about the clear sky shortwave water vapor feedback. And let's start with some basics. So the shortwave water vapor feedback simply arises due to the fact that, as for the long wave, we know that the shortwave water vapor absorption also increases with warming due to increasing water vapor concentration, leading to an increase in absorption with warming and therefore an amplifying feedback. We also know from global climate models that in the global mean, the magnitude of this feedback is roughly 0.15 watts per square meter per Kelvin for clear sky conditions, and roughly twice that value for all sky conditions due to reflection of radiation by clouds. However, what is much less clear is how we get from this very basic process understanding on the left to these concrete numerical values we get from climate models. And the aim of this work is to bridge precisely this gap between process understanding and complex climate models. And this seems like a quite obvious question to ask, looking at the recent literature, also listening to Sean's nice talk today. So we have recently seen a lot of conceptual studies that really helped us understand the clear sky CO2 forcing, for example, but also the clear sky long wave feedback, both regarding their magnitude, but also their state bit dependence. And but so far there has been no similar study on the shortwave water vapor feedback. And using many of these ideas, we present a simple model for the clear sky part of the shortwave water vapor feedback. And we compare it to more realistic reference simulation based on the 1D atmospheric model Conrad and the line-by-line radiative transfer model ARTS. So I will now present this simple model, and as you've seen, the underlying physics is actually quite simple, and so we can approximate this or represent this by a very simple one-layer model, which is shown here. So we have some, and I will first focus on the monochromatic feedback here. So that means feedback for one given radiation frequency, and we'll talk about how we get to the broadband value a bit later. So for a given frequency, we have some incoming solar radiation here on the top right that hits the atmosphere, and this atmosphere has a given optical depth tau, which we assume to be only dependent on water vapor. And then we know from radiative transfer that the fraction e to the minus tau will pass through the atmosphere. In reality, of course, we will get some reflection by molecules or aerosols or clouds for the all sky case. But for the clear scale case, it's actually quite a good approximation to neglect this. And then what happens next, of course, is that at the surface we have some surface albedo, and that fraction alpha of the radiation will be reflected, and then it passes through the atmosphere again, giving us another factor e to the minus tau. And with this, we end up with a very simple expression for the shortwave upwelling radiation at the top of the atmosphere. And this is really useful because the feedback is simply the change in this upwelling flux, and adding a minus sign here so that the amplifying feedback is positive as we define it here. And we can plug this in, and in our model here, we only have one temperature dependent term here, as we neglect any temperature dependence of the surface albedo, for example, because we don't look at the surface albedo feedback, but only at the water vapor part of the shortwave feedback. And so the only temperature dependence part here really is the e to the minus 2 tau term. And so to perform this derivative, we need to come up with some way to represent tau, and in a idealized way. Unfortunately, people have thought about that before, and one straightforward approximation one can make is by approximating it as a product of some column mean absorption cross-section kappa and the water vapor column m. And this water vapor column m can in turn be written as a function of temperature using the Clausius-Clapeyron equation. And if we plug this now in, we can perform the derivative and end up with this slightly longer expression, which is now an analytical expression for the clear sky shortwave water vapor feedback. And you can see some probably expected things, such as it's proportional to the incoming solar radiation, proportional to surface albedo. What's maybe less obvious is that you get this Clausius-Clapeyron term L over T squared here. So from this we get actually a inverse temperature dependence. But what I want you to focus mostly on here is the dependence on tau, which is this product tau times e to the minus 2 tau. And we can actually just plot this, this expression as a function of tau. And this is shown here in the black curve. And you can see that this expression is maximal at value of 0.5. But it also has substantial values between roughly 0.1 and 2. And what this implies is that the feedback is peaks for an optical depth of 0.5, but it's also substantial for values between 0.1 and 2. You can, if you want, you can also think of this as the equivalent to Sean's Goldilocks region. So this is also the transition region between optically thin and optically thick regimes. And this actually also holds up remarkably well. If you look at the green curve, that's what we get if we perform full radiative transfer simulation. So this is really the core mechanism that we find. And this is also interesting because, as we've just heard, in long wave emission, we often talk about this tau equals 1 law, and here we get a similar tau equals 0.5 law. And this factor of 2 simply comes from the fact that the radiation is reflected at the surface, and so it passes through the atmosphere twice, and so that increases, of course, the path through the atmosphere. So that's now for the monochromatic feedback. But how can we get a broadband feedback from this? And well, we can just spectrally integrate this, and the only spectrally dependent variable is the water vapor absorption, which is plotted here in this logarithmic plot. And this is a quite complex spectral dependency. And for now, we want to keep our model analytical. So what we do is also sorting this spectrum from the highest value to the lowest. That's this solid or this thick dark red curve. And then we fit an exponential function here in blue, which captures the first order dependency on wave number. And what this allows us now is idealized representation of the spectral dependency of the feedback. And that's shown here in the bottom plot. So for every wave number in the shortwave spectrum, I plot here the shortwave feedback for 3 different temperatures. The blue is for cold temperatures, red is for intermediate temperatures, and yellow is for high temperatures. And what you can see is that for any given temperature, only a small fraction of the spectrum actually contributes to the feedback. And we can also be more precise about this if we compare this to the top plot, where I now plot this spectrally resolved optical depth. This region exactly corresponds to the part of the spectrum where we have an optical depth of around 0.5 within this transition region or Goldilocks region. And so this behavior directly pops out of the equation that we have derived. And we can now spectrally integrate this, and this gives us now the broadband shortwave water vapor feedback. And first I want you to focus here on this value at 290 Kelvin, the global mean temperature. So I've plotted here in the black dot is a reference value from Soden et al., who only gave a global mean value. In blue, you see our exponential model, and in green, you see our reference simulations. And at the global mean, you can see the 3 agree quite well. But of course, also quite obvious is that the temperature dependence between our exponential model and the more realistic simulations is very different. And so clearly the exponential model is missing some crucial effect. And so to investigate this further, we now drop this exponential approximation and directly incorporate this spectral dependency in our model, and then perform our integration numerically. So this technically makes this part of the model not fully analytical anymore. But if we do this, we get this dark red curve instead. And there's 2 things you can immediately see here. So the first is that compared with this green line of the reference simulation, we get an underestimation. I would like to postpone this to the Q&A. And instead I would like to use my remaining time to demonstrate what the underlying factor is, why we get this increasing feedback with temperature, which is captured in the spectral model, but not in the exponential model, because it's not super obvious what this mechanism is, in my opinion. And so for this, we can come back to the same plot that I showed before. So on the top is the optical depth spectrally resolved for 3 different temperatures. And on the bottom, the shortwave feedback. And in solid is again the exponential model, but I've now added here in the dotted lines what happens if you plug in the actual water vapor spectroscopy. And for better visibility, I've sorted it again from the highest to the lowest water vapor absorption values. And if you now look at the bottom plot first, you can see that going from the cold temperatures in blue to the intermediate temperatures in red to the high temperatures in yellow, this peak gets wider, or in other words, the fraction of the spectrum that contributes to the feedback gets wider with increasing temperature. And this is because if we now look at the top plot, we can see that at low temperatures, there's only very few wave numbers that have the high enough absorption cross-section that we need, because at low temperatures we have very low water vapor concentration, so only very high, very absorptive wave numbers are able to even bring the optical depth to a magnitude of around 0.5. And those are around the center of absorption lines, so relatively few. And if you compare this to the yellow line, in the warmer and moister atmosphere, we have, of course, we need much less, much smaller values of the water vapor cross-section to get to the same optical depth overall. And these are much more common. And so this gives us a much larger fraction of the spectrum that contributes to the feedback. And this is precisely the reason why we get this increase of the feedback with temperature. And this effect actually dominates the effect I mentioned at the very beginning, that the Clapeyron radiation alone actually induces a negative temperature dependence, and this comes to pass at very high temperatures, but like at terrestrial temperatures, this effect of more wave numbers contributing as temperature increases dominates. So with this, I come to my conclusion. So we present a simple model for the clear sky part of the shortwave water vapor feedback based on a single one-layer model. From this, we see that the part of the spectrum with an optical depth of around 0.5 has the maximum value of the feedback, with a range around that contributes. When we approximate the water vapor spectroscopy by an exponential, we are able to capture the magnitude of the global mean feedback quite well. But it fails to capture the temperature dependence. For this, we need to account for details in the water vapor spectroscopy, as I've just shown. If you want to learn more, you can check out the paper here. You can, of course, also reach out via email, or I'm also happy to take questions now.
Awesome. Thanks, Florian. Do folks have any questions? We have time for a couple questions before the end of the hour. Feel free to raise your hand or unmute yourself. Toss it in the chat. Nodder.
Hi, Florian. Great talk. I'm just wondering, so the clear sky number is not quoted that often. Obviously, it's a first step in understanding this, and this seems like the appropriate level of simple model. Have you thought about how hard it would be to incorporate the albedo to clouds, which presumably is what causes the all sky number to be higher? It's just that you have a higher albedo overall. And could you get to that 0.3 number with just a little bit more complexity in treating the cloud albedo?
So yeah, we've thought about that, and the reason we didn't include it is because we didn't come up with a good way of an idealized representation of what the clouds contribute, because you need to look like you can have cloud overlap, you have cloud microphysics, and all these sorts of complications that are really hard to pin down in any idealized way that is still useful. I think the way forward would be probably to do a bit more empirical assessment, where you can test out different scenarios for cloud microphysics, cloud overlap, and probably come up with some reason for this roughly factor of 2. I mean, this seems to indicate that roughly clouds have the effect of doubling the atmospheric path of radiation. So I don't see a really straightforward and analogous way to do that, but maybe more along the lines I've mentioned.
Okay, thanks.
Okay. Well, we are at the top of the hour. So let's thank Maya and Sean and Florian again. It's a great set of talks. We will be coming to you next month, so keep an eye out in your inbox for the next symposium, the 46th. And with that, thanks everyone for coming. Have a good one. Bye.